Hi, welcome. This is complex analysis, series of lectures on complex analysis. Now we are going to start a new series that will be on isolated singularities. Unlike many textbooks and teachers, we will not define isolated singularities using Lorentz series. We will give it qualitative definitions and prove all the important results about isolated singularities using our definitions. Later we will introduce Lorentz series and characterize these isolated singularities in terms of Lorentz series also. Okay, so you will find it much easier. Let's get started. See, the basic trick is, suppose I have an open set U and a function f from to C, but it may not be defined, let us say, at some point. Okay, and suppose f from U minus this to C is holomorphic. Okay, what might happen is we may not know whether f is defined at A at all. Okay, or it may be defined, but we may not know about whether it's holomorphic on all of U. Then we want to say U is an isolated singularity. We want to define it. Let us define it carefully. Okay, just let me see whether I screen shared. Yes. So let us make a definition. Okay. Whenever we write BAR, this is the so-called deleted open disk. That is, okay, punctured open disk. You take the open disk centered at A with radius R, but remove the center A. Okay. Then suppose I have a function f which is defined from BAR. Notice that this is an open set. Okay. To see, this is holomorphic. Okay, then I say f has an isolated singularity at z equal to A or at A. Okay, so the same thing, suppose I have a function f. Okay, and perhaps U minus singleton A to C. I say f, okay, has an isolated singularity at A if the same thing happened, that is, there exists an R such that BAR is contained in U and f is holomorphic from the punctured disk to C. Okay, is the definition clear? Okay, but I can, okay, we can be mischievous. Why? Suppose I have a function f which is holomorphic from BAR to C, right? Now f of course is holomorphic from B dash A R to C, right? Therefore, can I say A is an isolated singularity? That is, I am hiding the fact of A, of f. That is, I am hiding the fact, the behavior of f at A, right? But technically, I can still say that. But even though this is not a genuine singularity, okay, this is a fake singularity, or it's not a genuine. But our precise definition allows us to say this. Still, I can say f has an isolated singularity A, but it is fake because I am not giving the full fact. That's the reason. Okay, so let us go back. Now, is the point clear? Right? What all I know when I want to say A is an isolated singularity of f. Okay, there is an open disk. Okay, in the deleted disk, that is punctured disk B dash of A, or F is holomorphic. That's all I know. I do not know whether F is defined at A, okay, or F is differentiable at A, etc. I have no idea. Okay, it may or may not happen, but still I will say it's an isolated singularity. Okay, right. So what are the possibilities it can happen? See, whenever I do not know what is F at A, I don't know why it happened. Right. So whenever I do not know how F at A is defined, right, what are the things what is the natural tendency for any analyst to look for? One should look for what happens to the limit as z tends to A of Fz. Okay, we want to investigate. Is that clear? This is a very natural tendency. Now what can happen? Three things can happen. That is, the limit z tends to A of f of z exists as a complex number. Right? So let us recall, what does it mean? There exists a complex numbers C, so that, okay, for every epsilon positive there exists a delta positive, so that 0 less than mod z minus A less than delta implies mod f of z minus lambda is less than epsilon. Okay, this is the definition. Okay, this is one possibility. And what is the second possibility? Second possibility is limit z tends to A of fz is infinity. What is the meaning of this? Okay, if you had followed my lectures on limits in real analysis, okay, you will know how to do this carefully. Okay, but for the time being, let me just look at the definition. Okay, what is the definition? This means for every m positive there is an r positive, so that for all z with mod z greater than r, mod fz is greater than m. We follow that? So this is your okay, this may be your b dash ar. Okay, sorry, yeah, I'm sorry, here what I want is, yeah, sorry, let me, this is wrong. What I want to say is limit z tends to A, right? So for every m positive, okay, what do I want to say? There exists a delta positive, so that 0 less than mod z minus A less than delta implies mod fz is greater than m. See, it's good that I try to draw picture so that I got it correctly, right? So this may be my BAR, this may be my A, then okay, so this is my F and this is my thing. So now you give me an M, okay, this is M, right? Then this is my delta. So whenever z lies in this delta neighborhood, then mod fz will lie outside this. That means f of z lies outside this disk. Okay, so pause, review, proceed. And what is the third possibility? Limit z tends to A of fz does not exist. Is that clear? So these are the only possibilities. Notice that these are mutually exclusive. These three cases are mutually exclusive. What does that mean? It means if one of them happens, the other two cannot happen. If the limit z tends to a of f of z is infinity, then it cannot be finite, right? It may not be a complex number, and you cannot say the limit does not exist. You follow that? And so if one of them happens, other two cannot happen, and not only that, one of them must happen. Okay, that is limit z tends to a, either it exists as a complex number or it has to be infinite, or these two things cannot happen. That means limit does not exist. Follow that? This is very crucial for you to understand. Please understand that. In case 1, we say it's a removable singularity. If 1 happens, that is limit z tends to a of f z is exists in C, then we say z equal to a is a removable singularity. Okay, why do I call it removable? That means I can define f of a to me the limit z tends to a of fz. That is, I can define f a equal to limit z tends to a of fz. Okay, then f becomes continuous, and remember f is continuous on all of BAR, and it is holomorphic on B dash of AR. Therefore, by our one of the Morera's theorem or extended Cauchy theorem tells us f has to be holomorphic. You follow that? This is so. Therefore, it's a fake singularity. It's not a genuine singularity. That is why we call it removable singularity. Please understand. Okay, why we say this? Because if you define then f is holomorphic, I have defined now BAR to C, this becomes holomorphic. Why? Either Morera or extension of Cauchy theorem. Okay, therefore it's actually not a singularity. It simply means we did not know what was FA. That's why we were struggling. Okay, we thought z equal to a may be a singularity. Please understand. Please go through this, play the video again if you want. And if 2 happens, that is the limit z tends to a of fz is infinite. Okay, then we say, okay, z equal to a is a pole of f. In case 3, that is limit z tends to a of z does not exist, we say z equal to a is an essential singularity. Okay, so pause, review, proceed. Now I am going to give 3 typical examples. The first one is f of z sin z by z for z not equal to 0. Therefore, z equal to 0 is an isolated singularity, because f is holomorphic on C star. Right? Okay. But if you remember calculus, you know limit z tends to a of sin z by z, you would like to say it's 1, therefore I can define f of 0 equal to 1. Right? But you know this only for real numbers, sin x by x, but we are dealing with complex numbers now. Right? So I have to prove that. But recall sin z is starts from z minus z cubed by 3 factorial plus z power 5 by 5 factorial, etc. Right? Therefore, sin z by z is 1 minus z squared by 3 factorial plus z power 4 by 5 factorial, etc. Right? Therefore, this goes to 1 as z goes to 0. Do you follow that? Therefore, limit z goes to 0 of sine z by z equal to 1 exists. Therefore, z equal to 0 is a removable singularity. Right? The second thing is, suppose you fix an a complex number, look at something like, let's say 1 by z minus a to the power n, where n is greater than or equal to 1. Right? Then this is holomorphic on C minus singleton A. Alright, therefore z equal to A is an isolated singularity. I say this is pole. Why? As z tends to A, mod z minus A goes to 0, therefore 1 upon mod z minus A to the power n, since n is greater than or equal to 1, goes to infinity. Right? This is by real analysis. Therefore, this is a pole. Okay. Now, third, let us look at f of z equal to exponential of 1 by z, z not equal to 0. Again, on C star, this is holomorphic. Alright? Okay. So, therefore, z equal to 0 is an isolated singularity. Okay. Now this is neither a pole nor a thing. How do I prove that? So I have to prove limit z goes to 0 of e power 1 by z does not exist. Right? That's very easy to prove. Let us look at when e power w equal to I. Right? So that means, let us say there's e power, let us say it. Therefore my t has to be pi by 2 plus 2n pi. Alright? This is my I, so I have to go pi by 2. Right? Therefore, are you following? Therefore, if I look at my zn equal to 1 by I times pi by 2 plus 2n pi, maybe I here, let me just check here 1 by z, it should go up, therefore let me say 1 by that, yeah, right. Therefore e power 1 by z n will be e power I pi by 2 plus I 2n pi, this is minus I, right. Are you following? It is equal to plus I. Right. Notice that zn goes to 0 and f of zn is equal to I for all n. Therefore f of zn goes to I. And similarly now you can look at minus 1, then I know e power I pi is minus 1. Therefore I can take my, let us say wn to be 1 by pi plus 2n pi, that is 1 by 2n plus 1 times pi. So wn equal to, not thing, wn equal to pi plus 2n pi or 2n plus 1 pi, right. Therefore e power I, maybe I times put I, sorry, I am wn equal to I times pi plus 2n pi, that is I times 2n plus 1 pi, right. Therefore e power 1 by wn, yeah, and there you are right, I am sorry, this has to be 1. Okay, I want wn, right. Therefore this is going to be e power I pi plus 2n pi, that is equal to minus 1 for all n. And again notice that Wn goes to 0 and f of Wn is always minus 1, therefore limit of f of Wn is minus 1. So this shows limit z go to 0 of e power 1 by z does not exist. Therefore z equal to 0 is an isolated singularity. Right? Okay. Now before we go further, before we prove results about today's lecture, hopefully I will concentrate on removable singularity and prove one of the most important results in this about removable singularity. Before that, one should not think every singularity is an isolated singularity. Okay, for example, let us look at sine. This is a very standard example. Okay, let me see sine. What do I want? I want it to be isolated singularity. Therefore, let us look at sine z is 0. That means z equal to some 2n pi. Of course, n pi also, but it's good enough. I'll make it 2n pi. Right. Therefore, 1 upon 2n pi I have to do. So let me look at sine. Okay, 1 upon z. Okay, now z equal to 0. Z equal to 0 is a singularity. What do I mean by singularity? That means, okay, I do not know how it is defined, right? Because sine 1 upon 0 I do not know how to define, so I am calling it a singularity. Okay, I have not defined that anyway, okay, intuitively. But remember that, yeah. So if I take z equal to 2n pi, zn equal to 2n pi, therefore, okay, 1 upon zn, okay, will be, okay, 1 upon 2n pi, therefore 1 upon 2n pi will be 2n pi, therefore sine 1 upon zn is not defined. No, I am making some mistake here. What do I want? I want 1 upon 0, right? Yeah, that's correct. Yeah, 1 upon this is not defined. Sine 1 upon z is defined, but this is not defined, right? But notice that z's are 1 upon 2n pi and it converges to 0. Therefore, there exists no r positive so that, okay, the function is holomorphic on B0R. Yeah, because z equal to 0 is a cluster point of all these follows. Do you understand that? I hope I made my point clear, because I hope you are not confused, right? I forget to write 1 upon or something. Okay, I am more worried about explaining, so I get it, right? So intuitively z equal to 0 is a singularity of 1 upon sine 1 upon z. Okay, but it's not isolated singularity. Yeah, this is example number 1. There is another example also. Okay, example number 2 is, let us look at log of z. Okay, and let us look at some B0R. Okay, then you may think log 0 is not defined, therefore this must be some kind of a singularity. But this is not isolated singularity. Why? Because in any neighborhood of 0, okay, log is not defined as a continuous function. Remember, because the only way I can define here it's a continuous function is I have to delete one semi-axis. If you had gone through my lectures on logarithm, you will know that, right? So log is, see, what do I want? I want it to be holomorphic in a punctured disk around 0, but it's not. You cannot even make a continuous definition of log z in any punctured disk around 0. Therefore, it's not even isolated singularity. Even though it looks like a singularity, yes, you are right, but it's not isolated. Keep these two things because many teachers will avoid. But if you want to master complex analysis, you should also learn there are other singularities, how to deal with them, how to differentiate them from isolated singularity. Okay, PRP. Now we are going to prove one of the most basic important result on removable singularity. This is already proved as a corollary to Muraria's theorem. So now I am going to indicate a proof. At that time we did not have, okay, a full power series expansion kind of thing, but we were able to prove this. Okay, just to look at, I do not remember the video number, but those of you who can identify in the comment, please give a reference to where it is proved. So what is the theorem? The theorem says, suppose f is defined from some deleted neighborhood BAR to C, okay, assume this is holomorphic, and limit z going to a of z minus a into f of z is 0. Then f has a removable singularity. In fact, there exists a holomorphic function g from BAR to C so that g of z equal to f of z for z in BAR z not equal to e. That is, it is actually a restriction of a genuine holomorphic function. It's just a mistake. We did not know how to define f of a perhaps. That is why we thought it is a singularity. Is that clear? Is the theorem clear? Okay. Yeah. That. So this is what I said. Why it's a removable singularity? When I define removable singularity, I already said that. Why it's called removable? I can define f of a suitably so that f actually becomes holomorphic on the entire disk, not necessarily only on the punctured disk. So we can prove. So it just gives a condition to recognize such a removable singularity. Yeah. Notice that when can it happen? For example, as a corollary, suppose f is bounded on b dash a r, then limit z tends to a of z minus a into f of z is 0, right? Obviously, and therefore z equal to e is a removable singularity. Of f, right? So these are the two easy ways of Okay, working with removable singularity. Either limit z tends to a of z minus a f of z is 0, that is a more powerful one, the strongest one. But a weaker thing is if f is going to be bounded in a deleted neighborhood, that is in a punctured disk around a, then also z equal to a is a removable singularity. Okay, let us go through the proof. Define phi of z equal to z minus a into f of z. Okay, for z in b dash a r and equal to 0, that is what phi of a. Right. So now what do I know? This means, therefore this implies phi is holomorphic on b dash a r and phi is continuous at a, and therefore by extended Cauchy, phi is holomorphic on BAR. Remember, extended Cauchy goes as set over in a triangle. Okay, if I take the boundary, if I take the path integral of phi over the boundary, it has to be 0. We proved it. That's extended Cauchy-Gursa, and therefore we know phi has a primitive. If phi has a primitive, call it psi, then psi dash equal to phi, but psi is holomorphic, therefore psi is infinitely differentiable, therefore phi is also differentiable. That's how we concluded. So do you remember my policy? Whenever that small things come, try to recall as much as possible how we proved it. That way you become master. You don't have to say I have to every time remember. Try to repeat this, review this whenever possible, then it becomes part of you. Anyway, right? Okay. Now that I know phi is holomorphic, I would like to know what is phi dash a. Phi dash a by definition is limit z to a of phi of z minus phi of a by z minus a. I'm sorry, let me put it z squared. Yeah, it's not z minus a, z squared. You will see the reason why. Okay, see, this is how I learned. See, right? Now phi of z is z minus a whole squared into f of z minus phi of a is 0 by z minus a, and I want to say limit z to a. So if I had z minus a, then they will cancel, then limit z tends to a of f of z. I do not know what it is. But when I put z squared, then this becomes easy. This is going to be limit z going to a of z minus a into f of z by hypothesis, that is 0. Do you see the beauty? Why I put not z minus a, but I put z squared. Remember, my earlier argument is still correct. With z minus a into f of z, phi is still holomorphic. But I may not be able to compute phi dash 0. But now I was able to compute phi dash a. Do you see the beauty? Yeah. Right? Therefore, I know phi dash a is 0, and that is also equal to phi of a. Since phi is holomorphic, okay, on BAR, I can write phi of z in powers of z, that is C0 plus C1 z minus a plus C2 z minus a whole squared, and so on. Right? But remember, this is nothing other than phi of a, and this is phi dash of a into z minus a, etc. Right? These are all 0. Therefore, this whole thing is going to be C2 z minus a whole squared plus C3 z minus a whole cubed, and so on. That is, this is going to be, so I can write z minus a whole squared, I can take it as common and write it as n greater than or equal to 2 of Cn z minus a to the power n minus 2. Right? Are you following? So notice that phi is holomorphic, there is this entire power series converges. Therefore, if I denote this by g of z, or maybe call it psi of z. Okay, maybe call it g of z. I think that will be good. Okay, so I don't know what I want, but let me call it psi, then I will change, because I said there is a g, so that g restricted to the function disk is f, so I do not know whether that is the g I want. Okay, as I said, I do not remember the proof and write. Okay, that's a problem, right? Let's call it psi of z. Therefore, this is z minus a whole squared into psi of z. Now psi is holomorphic on BAR. Are you following? Yeah, right. Now what do I have? I have phi of z equal to z minus a whole squared into psi of z, right? But what is phi of z for z not equal to a? For z not equal to a, phi of z is f of z into z minus a whole squared. Therefore, phi of z for z not equal to a. Have you understood this? Yeah. Therefore, z for z not equal to a, f of z is nothing other than psi of z. But psi is holomorphic on BAR. Therefore, define, okay, f of a to be psi of a. So this psi is what is g. Okay, call psi as g. That's it. See, I did not know whether this is what I wanted. Have you understood the proof? The proof is extremely simple. Yeah. So therefore, limit z tends to a of f of z is same as limit z tends to a of psi of z, but that is psi of a, because psi is holomorphic in particular continuous. Therefore, psi of a. Therefore, this limit exists, and that limit is psi of a. Are you following all these things? Therefore, we have proved. Okay, z equal to a is a removable singularity, and how do I extend? I extend f of a by setting psi of a or g of a. Is it okay? Pause, review, proceed. Let us try to understand this argument in depth. That is, have a closer look. Okay, because it's going to tell us how any removable singularity is going to arise. Isn't it beautiful? See, suppose, so I need some definitions. So let f from u to c be holomorphic. Okay, and f is not identically 0. Right? Suppose f of a is 0. Yeah? Then a is an isolated 0. What does that mean? That is, there is an R positive, so that BAR is contained in U, and so that if f of z equal to 0 for some z in BAR, implies my z must be equal to a. That is, the only 0 in the open disk BAR is a, and if z is not equal to a, then f of z is not 0, at least for z in f of a. Therefore, it's isolated. Okay, there is only one point. You understand that? Yeah. Okay. Now I want to say, do you remember in a polynomial we say something alpha is a repeated root or multiplicity? With the multiplicity m. What does that mean? That means if p is a polynomial, I can write p of x as x minus alpha to the power m into some q of x, so that q of alpha is not equal to 0. Right? Do you remember? So we want to define multiplicity of an isolated zero of a holomorphic function. Okay, so z equal to z is an isolated zero of f. Okay, holomorphic function. Right. Then I say, okay, the order of 0, or now you in analysis we will use the word order. Order of 0 of f at z equal to a, or order of z equal to a as 0 or whatever it is. Okay, order of a as a 0 of f. Okay, I say it's m if, what do I want? Okay, there are two ways of defining. Let us look at f of z. Okay, then expand it in powers of, let us assume some behaviour is an isolated 0, therefore there is an r positive such, but therefore the only 0 of f in behaviour is a. Right, let us assume that, therefore f of z I can write it as summation cn z minus a to the power n is from 0 to infinity, right? But remember, f of a is 0 means c naught is 0, right? Therefore I can write, let m be the smallest integer, non-negative integer, so that cm is not equal to 0. That is, c naught is 0, c1 is 0, and cm minus 1 is 0. Okay, these are all 0, and cm is not equal to 0. Therefore I can write f of z as, okay, cm z minus a to the power m plus cm plus 1 z minus a to the power m plus 1, and so on. Therefore again I can write it as z minus a to the power m into summation cn z minus a to the power n minus m, where n is greater than or equal to m. Notice that this is exactly what we did in the case of our phi of z earlier. In the removable singularity phi of z we wrote as z minus a squared into psi of z. Do you remember that? That's what I am imitating here. Have you understood this? And this, if you call it g of z, okay, then g is holomorphic and behaviour. And what do I know about g of a? G of a is c of m, but that's not equal to 0. Do you understand this? Therefore I have written f of z as z minus a to the power m into g of z with g of a not equal to 0. So let us summarize. If z equal to a is a 0 of order m for the holomorphic function, isolated 0 of course, for the holomorphic function f, then okay, f of z is of the form z minus a to the power m into g of z with g of a not equal to 0 and g holomorphic on behaviour. Okay, pause, review, proceed. Okay, let us make a digression. I need only this, whatever I am saying now, but it's always good to know a digression also. Now, when I say order of 0th order of a for the function f equal to m, then in that power series expansion, okay, we saw that c naught equal to c1 equal to cm minus 1 equal to 0 and cm is not equal to 0. But remember, there is an intimate relation between cn and nth derivative of infinity, right? This is like n factorial. Okay, therefore it means, okay, z equal to a is a 0 of order m for f if and only if fk of a is 0 for 0 less than or equal to k less than m, and the mth derivative of f at a is not 0. Are you convinced? Okay, this is an equivalent way. If you remember, for repeated roots and polynomial, that's what you do. Alright, z equal to x equal to alpha is a repeated root if f dash at alpha is 0. Do you remember that? It's a multiplicity 2, then f dash alpha is 0. If multiplicity 3, f of alpha is 0, f dash alpha is 0, f double dash of alpha is 0, etc. Right? It's exactly similar. Okay, pause, review, proceed. So now I am ready for the thing. Now suppose I have a function f which is holomorphic and a belongs to u and a is an isolated 0. Let us say BAR containing u, right? Then let's look at the function of order, let us say of order m. Let us look at the function g defined by g of z equal to f of z by z minus a to the power m, or z not, okay, z in BAR and z not equal to a, right? Then g is, okay, z equal to a, g is holomorphic on b dash AR and z equal to a is an isolated singularity. Right? Maybe I will call it as phi of z. Okay, then phi is holomorphic and isolated singularity of phi. Right? I claim z equal to a is a removable singularity of phi. If you had followed my argument so far, this will be easy, because since z equal to a is an isolated singularity, isolated 0 of order m, okay, there exists a holomorphic function g in BAR. It's a holomorphic on this, okay, and such that f of z is z minus a to the power m into g of z with g of a not equal to 0. Right? Therefore, my phi of z is f of z by z minus a to the power m is nothing other than g of z for z not equal to a. But this is holomorphic on BAR. Therefore, z equal to a phi, okay, phi can be extended to a holomorphic function on all of BAR. Therefore, phi has a removable singularity at z equal to a. Is that clear? Pause, review, proceed. Now we can go one step further. With that I will stop. Now suppose, okay, I will just don't want to write everything. I think all of you understand what I want to say. Okay, f and g are holomorphic functions from one open set U to C. A is contained in U, and A, this is A is an isolated 0 of f as well as g in BAR. It will be BAR1 and BAR2. Take R to be minimum of R1 R2. Then on BAR, the only singularity, isolated 0 of f will be A, and similarly isolated 0 of g will be A. And let assume their orders are m and n. Now what is the question I think I should ask? I hope all of you know now, right? Let us look at f of z by g of z. Okay, now this is holomorphic on b dash ar, because the only singularities for phi of z will be where g of a is 0, but okay, and on b ar the only zeros of g is at z equal to a, therefore on b dash ar this is holomorphic, right? Therefore z equal to a is an isolated singularity. Phi. Now what kind of singularity? Now let me write. I think this is what I should have used. It would have been easier for me. Let us write f1 of z so that f1 of a is not 0 and f1 is holomorphic. And similarly g of z you write as z minus a to the power n g1 of z, and that's that g1 of a is not equal to 0 and g1 from bar to c holomorphic. Therefore my phi of z is going to be f1 of z by g1 of z into, okay, z minus a to the power m minus n. Yeah, for z not equal to a. Now what kind of singularity I can expect? Now all of you know, remember, at as z tends to a, phi of z limit z tends to a, okay, let us say f1 of z by g1 of z is f1 of a by g1 of a, because g1 of a is not 0, therefore it's a finite number. Therefore the problem comes only here, and if m is greater than or equal to n, then I am through. Yeah, why? Because if m is greater than or equal to n, then I will have a limit of that will be 0, right? Therefore I will have removable singularity, right? If m is greater than or equal to n, then z equal to a is a removable singularity of phi. Okay, please go through this, and this explicit discussion of removable singularity is not dealt with carefully, and this will be needed in the next session on poles also. Please learn that very well. Go through the last portion after the removable singularity, Riemann's theorem of removable singularity. We went through the proof, understood what is happening, and we generalized that argument. Okay, that is very interesting. If you had understood that, you will see dealing with isolated singularities become much easier. Yeah, okay, I hope you enjoyed the lecture. We will meet again. Take care, stay safe.